welcome to Module 13, in which we talk about missingness, duplicates, and outliers. So why does this module matter? Many data science tasks, deployments, failures happen before anyone actually trains a model. Obviously, we're getting to the point where we can start taking our data and learning sort of systems around those data. But for the time being, we still have to realize that those systems exist inside of a context. And if the context is faulty in some way or wrong, we have the wrong process, then the overall system is going to fall apart. Okay, so we need to do the simple things, the contextual things, we need to do that correctly. In the real world, the data are not going to be clean, typically. They're going to have maybe holes in the data, to speak very loosely. This can mean just that data does not exist. It hasn't been given to us when we thought it should exist. There might be some weird or impossible numbers. So occasionally, like the specific number that you have in your data set is not exactly what it should look like. It's a bit higher or lower. It just doesn't seem totally correct. And occasionally there can be recording errors also, to the point that it's impossible, right? So if you're measuring someone's heart rate, for example, and they're alive, but their heart rate goes up to like 1,000 beats per minute or something, obviously something might be wrong, either in the sensor or in the recording of the data and so on. Sometimes when we're combining two data sets together, which is often the case, will result in these clone rows where systems sync badly. So there'll be multiple data points that are exactly the same thing. There might be extreme points, that might be mistakes. So you might have a data point that is not like 1,000 beats per minute, but it looks like something extremely high, way higher than all the other data that you might have in your data set. So what does this mean? Is this also an error, or is this like a real recording that just happens to be very different than the other ones we have so far? And how can we tell the difference with just looking at the data itself? So if we ignore these kinds of problems, then our model will, like whatever the system is, will happily learn patterns that has typos in it, broken sensors, half-recorded events. It'll learn noise, and it won't necessarily learn like the actual behavior or phenomenon that we're actually trying to attend to in the first place. So this module will be about learning to notice and question these problems before they actually, wreck your conclusions. So there are a couple of different lenses we can apply to what data quality means. And these terms can also be changed around a bit. The terms don't matter as much as the concepts behind them. So I'll just go through them. The first one is accuracy. Does the value reflect reality? So this is important, obviously, like if we're trying to learn something about the environment and make decisions in the environment, if the data doesn't really reflect the environment or reality, then we're not really measuring what we think we're measuring. Precision is a different idea. Precision in this context is how finely is it measured. Occasionally you can get data sets from some websites where they give you information about like a population in aggregate. This is the average age or the average income in this massive region, but it doesn't necessarily tell you very much about the details in that region. Okay, so like the precision should be as precise as possible for the task you're trying to accomplish. How complete is the data? Are values simply not there? Is everything consistent? So are the formats or units or states actually aligned properly? If you're looking at, say, volumes, or you're measuring in terms of cubic centimeters or in milliliters. Timeliness, so are the data current enough? Again, if you're working in Nova Scotia Health and you want to build a data science application to help assess for risks related to breathing disorders, if all of your data comes from the 1980s or 90s or even the 2000s, the early 2000s, that might not be timely enough to deal with current respiratory illnesses. How believable is it? This is a bit of a kind of a qualitative one, but do you trust who recorded it and how it was recorded? This is something we don't need to get into too much detail right now, but Even if someone recorded data with good intentions, it's possible that they recorded it in a way that took some shortcuts accidentally, or because they didn't have the resources to acquire things more fully. So just because you have a set of data that seems accurate and precise and complete doesn't necessarily mean that mistakes were made or were not made. Interpretability is also a little bit qualitative, obviously, but can humans understand it, right? So if all of your variables all have these very obscure names that, even if you know the names, are very hard to interpret what they actually mean, then the data become somewhat difficult to make use of. So this is a small kind of example from my own experience. I used to do a lot of work in speech data. So we use speech for a variety of cases, including speech recognition, maybe even diagnosing individuals with disorders of cognition. And the features had names like the second derivative of a 13th Kestrel coefficient scaled with the Mel scale or something like that. And even though I know how that value is computed, like the actual meaning of the 13th Kestrel coefficient as opposed to the 12th doesn't necessarily carry too much like real world and intuitive meaning to it. Okay, so I mean sometimes that's fine. Sometimes you need to not be burdened by human cognition, but we still want to make choices, and those choices need to be informed in a way that we understand. There are various flavors of dirty data. Here's just a couple of them. There's inconsistent types, like I mentioned earlier. Like sometimes we might have a bunch of real valued numbers, but some of them might be measured in cubic centimeters, others in milliliters. And unless that difference is recorded somewhere, then that column will appear very, very strange to me. Inconsistent values, like maybe some of them are recorded with 2 decimal places, some with 0 decimal places. Like, why is this happening? Like, this is confusing to me, and I don't know why this difference occurs. It's a problem you want to avoid. Missing data, outliers, noise and recording errors. So one form of noise, like when you hear noise, you probably think of something like either signal noise, like you're listening to an audio recording, but there's a loud hissing sound. So that is a form of noise. That's like the most intuitive potentially. And that noise, that hissing sound, is sort of irrelevant, but it drowns out the signal that you actually care about. The second most common use of the word noise in data contexts might have to do with like noise online. So there might be an event that occurred in the news, and there might be a couple of posts online about this news event, but then there'll be so much extra stuff on there. So there'll be social media posts, misinformation, disinformation, videos where things have been doctored and all kinds of this nonsense, the yappity yap of talking heads on TV, and suddenly whatever actually happened is lost in all of this noise, right? So all this irrelevant data that masks the signal. Occasionally, in a very deep data science context, we'll want data to have labels on it, right? So we'll want to see, maybe we work at a store, like a bookstore, and we want to kind of make predictions about whether or not a person who entered the store will make a purchase of a certain type. So we want to maybe kind of promote something for that user. We know something about their previous buying habits. We know something about their maybe their income, or whether they subscribe to a newsletter, or all the kind of input information. And then we might have somebody who works for us who kind of labels like all of these individuals we have in our data set as people we want, like high value customers we want to promote for our products. Now, like if you have a person sitting in your office kind of providing labels for all of these data points, how do we know that they're not biased themselves? Maybe they look at this data and they just kind of think that, well, people who are between the ages of 30 and 50 are all the high value people. And maybe that's a subconscious bias, but that informs the labels that they provide. So when we get the data and we have all of these labels, which we think are the ground truth, maybe that's not the ground truth. Maybe like we're accidentally learning the bias that this particular labeler had on our system. We'll talk about how to deal with all of these kinds of problems in this course. So let's go to like one of our examples, this campus wellness check-in. So students can do this quick wellness check-in at kiosks. Maybe there's like a screen, a tablet. Maybe there's just an app that records sort of where they are, and then the clinical staff will enter some additional records later. So maybe there's like a student who meets with clinical staff. So we have the clinical staff data in one database. We have the check-ins on your app with saying how you're doing that particular day. And on the back end, we want to combine these two data sets together so we can get a more fulsome picture of how to help you. So every row will be one check-in event, whether it's in a kiosk or with a clinical staff. There's going to be a lot of variables. So there's going to be check-in IDs. Maybe these are missing from the system. Maybe a particular version of an app, failed to measure these. There's going to be a student hash. This is not so important for you, but this is sort of back-end stuff. A timestamp when it occurred, a location where it occurred, how many sleep hours they got last night. This could be something that they just sort of describe, what their stress is, what their temperature is. You could sky's the limit. My favorite one, notes, which is free text, which can be obviously very messy and full of spelling mistakes and typos and so on, which is yet another form of noise. So here's kind of a big fictional, I've put all this fictional data in rows, and I put these rows into a data frame, and then I've just kind of printed it out. So here's a sort of printout of the data. Here's a check-in ID, hash, timestamp, location, sleep hours per night, and so on. And you can see how. Right off the bat, you can see some challenges here. So, stress from 1 to 10. It's all good, but why is this one labeled -1? Like, what happened there? Resting heart rate seems to go from like the 60s to the 240s. That doesn't seem very reasonable. There's not a number included in terms of sleep hours per night. So just scanning this is one of the reasons why we like either using DF head, or in this case, I just put everything on because it's tiny, and just giving a quick visual scan of the data to see if anything is going wrong. In this case, obviously something is going wrong. So you can go ahead and look at it yourself also. You can spot some problems. I've identified a few of them. There's missing fields, there's off script or fake values. I should mention here that what this -1 means. Like if the app only allows you to move a slider from 1 stress to 10 stress, and that's all it can record, that's all well and good. But then maybe during the unification process of all these data sets, somebody had access to the raw data, the raw SQL or the raw spreadsheet, and then they saw, well, there's a missing value here, and we don't like missing value, so I'll put a -1 as sort of a placeholder for a missing value. And all of a sudden now we get the data and we have this integer value where we checked for types already, and it looks like it's fine because it's an integer, but it's not within the range, so what do we do about it? This can often be considered to be missing. There is a unit mistake, so I didn't spot that a moment ago, but you can go back and check it yourself. If you have a fever of 98.2 degrees Celsius, then there's seriously something very wrong, and I think probably medical help is beyond you at this point, but 98.2 is a reasonable temperature for the Fahrenheit. Fahrenheit is an old-fashioned form of measurement that nobody really uses anymore, as far as I can tell. The sensor glitches, so like this resting heart rate I kind of spotted was kind of way too high. So obviously maybe if there's a watch or some kind of other sensor that's measuring heart rate, it just failed at that particular moment. Also, there's some duplicates, so go ahead and try to find it. Like there's some same student and timestamp, more or less, but during a merge, they was combined into one data set. So try to find a duplicate just visually also. Okay, so this is very common. Now, one thing I should mention here for a moment is we have a list of a few dozen maybe data points here. So very quickly you could scan it visually and find some errors. But in real life, you might have millions of data rows in which it's way too time consuming for humans to look through. So we need an automated way of identifying these kinds of problems. And with all due respect to our species, we make all kinds of errors and mistakes. And it wouldn't be better if we had some kind of a tool that could go through the data and do things for us automatically and maybe not be prone to our cognitive biases. So first, missingness, data missingness. So there's some easy cases. So occasionally you'll see not in numbers or none or empty strings in text fields. This is all explicitly empty or missing data. Occasionally a human might enter in a placeholder, like I mentioned, a -1 for age. Nobody in this data set of university students will have an age of -1 or an age of 999. So this might be an instance where we would consider this to be missing also. Occasionally you have text. So text is not necessarily not a number in terms of Python wouldn't recognize the word unknown as not a number, but we would. So we might have to have a tool to look for synonyms of the word unknown in our data, and then kind of frame that as a missing data problem. So these are easy because it's very easy to automate each of these cases. You've probably thought on the top of your head, well, if you're trying to spot a missing data of this type in our data set from earlier, and you know that anyone in university is probably between the ages of, say, 16 if they're very smart to 100 if they're very eager to learn, then anything outside of this range can be considered to be not a number, and you just have a little loop that loops over the data and finds those instances. We'll see some other forms of automation soon enough. Sometimes harder to see is obviously if a person's dropped from a database entirely. So imagine somebody checked in a kiosk or on their app, but it wasn't transmitted to the central database, and then it just kind of lost that data. So technically they entered the data somewhere, but the data never made it to the central database. So how would you even know it's missing? Unless you happen to know that particular person and they told you or something like that. And even then, who knows? One system might always leave check-in ID blank. Another one might always fill it, right? So maybe just the versions of the software or where it's implemented might have slight behavioral differences that result in data sets that look different. Maybe the staff will skip certain questions. So they'll ask you question 3, and depending on your answer, they might skip over to question 10 or something like that. So you have a lot of missing questions in between. And similarly, different hospitals, different apps will just have different kind of subsets of fields that they care about. So you'll have all these missing components that you won't necessarily be aware of how they got there. Okay. So there's invisible decisions behind the scenes that if all you have is a spreadsheet of data, then you're missing a lot. So here's 3 ways missingness can happen generally. There's some classic categories. There's missing completely at random. So if the kiosk kind of randomly just turns off or doesn't send the data, then some things will be missing kind of totally at random. And that's sort of just picture a big table of results and just completely all over the place without any sort of rationale, and just some elements are just sort of missing, just kind of poked out of there. Missing at random. Now this is still kind of missing, there's still patterns that resemble kind of a widespread of this data that's not there. And it is random. It's still kind of probabilistic, like many things are in life. But they're dependent on something that if we just knew that hidden variable, then we would be able to understand why this missingness is happening. So if we knew that a clinical staff is always going to fill out the fields, then we'll be able to say something about any missingness that occurs in that column. Or if we happen to know that they'll always skip certain questions, then if those questions are missing in that column, then we have a reason for it that we can point to in our environmental model. This missingness, missing not at random. This is for people with high stress. They might skip the stress 1 to 10 field, right? This is actually very similar to the missing at random aspect, but if it's 100% of the time, then technically, if you want to be pedantic about it, it's still random. It's just 100% probability, but it's still it's fundamentally different than the other instances because you have a complete confidence that if this is the case in the world, then this is the result you're going to see in your data set. Sometimes missingness is not necessarily a problem, but it can even actually be useful to you. Sometimes no value is the value itself. Okay, in electronic health records or EHRs, if a lab like your blood work was never ordered, then this can be actually even more predictive than whatever value you get from that blood work itself. Okay, so if a patient has no cholesterol test from their blood work, okay, that means the doctor who they saw for that record considers them to have no cardiovascular risk, or at least a very low cardiovascular risk. Because if the clinician was worried, they'd order the blood work. Okay, this is actually a whole paper about this phenomenon you could look into. Patterns where labs stop being ordered after a normal result can also encode disease severity. So In cancer, for example, there's a bunch of cancer biomarkers that they can go very high. And again, you're doing blood work periodically to measure these biomarkers. And they gradually go down and down and down. And at some point in time, blood work will no longer be recorded. And you won't necessarily record 0 for these biomarkers. You'll record nothing because you're not even taking blood work at all. So this seems to be missing, like it seems to be, oh wait, there's some missing data here, but it's informative because now you know that, well, the doctor, like the oncologist who is tracking the progress of this patient, saw that the biomarker disappeared and no more tests was necessary. So now you can say something about their health. This is actually used in to stratify COVID patients. I mean, I mentioned it was not oncology, so it's not like a cancer biomarker, but the same general idea applied to COVID-19 and stratifying patients across multiple hospital systems. Sometimes labs, missingness is tied to disease burden. So if there's sicker patients, they get more labs. Like the doctor's worried about them, they're going to worry a ton of stuff to assess, what's going on. So the more labs that are recorded versus a small number of labs that are recorded, that's not just missingness, that's actually informative. Healthier patients will have more gaps in their records compared to less healthy patients. So that tells you something. If you're making a machine learning model to predict the outcome for a patient, missing data is not necessarily a problem in this case. So in prediction models, we'll talk about models and prediction a bit later in this course, but just to kind of get ahead of ourselves, one strategy can be to keep missingness as a feature. Don't try to just delete all entries of not a number, but actually use sort of like a missing indicator variable that for some variables like these, we'll just mark when the predictor is absent. It's not 0, it's just absent. And then if you can do that, then some experimental work, some simulation work shows that doing so can actually improve and not actually harm performance. So if you're interested, here's some papers that talk about that kind of phenomenon. So don't necessarily, if you see not a numbers or like empty fields strewn through a data set, like again, be reasonable and be thoughtful, and don't necessarily rush to fill in the blanks. We'll talk about that in a second, or like just delete those entries, because for some variables, like not measured is itself a signal about the clinical judgment, okay, and the workflow and the patient state, or whatever else, the same applies in different domains than just healthcare. But yeah, the signal can change once we start using it in deployed models. So always be careful. So you can do a couple of things for dealing with actual missing data, like of the kind that was problematic, like we saw initially. You can drop rows or columns. Okay, this is a bit of a heavy-handed method, but if you have tons of data, maybe, and only a small number of instances are missing, then maybe this won't be so bad. If you see a column or a row in your data set that is empty, just delete that data point. Okay, either delete that row, that data point, or delete that column, that variable, right? Because there's some problem here, I don't want to deal with it, so I'm just going to delete it. It's not necessarily the worst thing in the world to do that, like it, at the very least gets rid of the not a number, but it is a bit crude, okay? Another thing you can do is try to regenerate the missing values manually. You can do like a lookup, you can do call or review log. This is kind of not going to scale very well, but if you have a patient who was supposed to check in on their app on a particular time and you don't have their data, then it's reasonable in that case that a doctor might actually call the patient and ask them to tell them what happened in that data point that wasn't conveyed. So this is good, but it's also there's problems with it. It doesn't scale well if you have millions of patients you have to follow up on. And the third way is to fill in missing values automatically. This is called imputation. Imputation is filling in these missing values automatically. To do that, you probably need to have a good idea of what the data kind of should be in the first case. Okay. Each of these strategies can build assumptions to it. So what patterns are you okay to lose? Are you okay to lose this entire data point just to get rid of the not a number? Which values do you think are close enough? If I was going to change a not a number to a reasonably sounding data value, what is close enough? And will adding this value change my predictions in crazy ways? Again, be careful. So always, be aware of how you change the distribution of the data. So how do we go about dropping data? This is not quite as easy as it seems, although it's super easy. Some common heuristics are you can drop rows that are missing the target label. If you're doing supervised learning, you really need the target label, so just drop those. Maybe you can accept a small number of missing data for a particular row or a particular column, but maybe you have some threshold and you say, well, if more than 10% of this row is missing entries, then this is too empty a data point for me. It's too much like lacking. So in that case, because I have over some threshold of missing variables, like a certain proportion of the variables are missing, in that case I'll drop that row. So very easy, and you're not inventing any data, you're not synthesizing anything fake, but this can introduce bias. So it's possible that you might be in an environment where the hardest cases happen to have a lot of missing values in the columns of that row. Maybe the data comes from a certain population in which not all of the data are available. So you're going to start removing data points belonging to certain people in our society who don't have that much data. That's just going to introduce more like bias, like demographic bias. And of course, just fundamentally, and this is one of the reasons why I don't like doing this, is you end up losing information the model can use. I almost never like dropping in data. I think there's always some useful information there. Even if the signal is obscured by a lot of noise, then there's still probably something there that is still going to be useful to understand the relationship between noise and the signal that a model can make use of. So I don't like dropping data, but it is sort of a quick and easy hack to get rid of not in numbers and missing data. There are simple automatic fills, so you might simply replace missing values with a constant like unknown, and then in your modeling have to just deal with these unknown variables. Cheap and easy way to deal with the missing data is just take the mean or maybe the median of that feature, right? So you're going down your rows, and you get to a point where one of the columns has a missing value in it, okay? And I want that value. Everything else in this row looks very informative, but this one value is missing in the middle. Well, I can take all of the other values I have for that column, for that variable, and take the average. The average can be the mean value or the median value. Whatever that is, I'll plug it in there, right? And maybe that's a bad estimate for that particular data point. Maybe that data point otherwise is an outlier and it shouldn't be anywhere near the average. But at the very least, you know that doing the median or the mean will give you a value that's typical for that value without looking at any other information. Occasionally you can do this a bit more intelligently. So if you know that this row that you care about comes from a particular class, like this is an example of fraud that you're trying to identify, or this is an example of a person with this disease, you can, instead of taking the average over all of your data, you can just take the subset of the data that belongs to that class, maybe from other patients, other users, other sources, and then just take the average, like the mean or the median for that subset. So if there are differences between the classes that you're trying to identify, at the very least, now you're dealing with statistics that are more specific to this row with the missing data in it. So this, again, is super easy. There's something called simple imputer in scikit-learn, which we'll see more later, which can do this to you in one shot. It's super easy. Keeps the overall data set nice and simple. One problem is it kind of shrinks variance. Variance, like the variance of your data, can actually be helpful. And if you have a lot of data, like a lot of missing data points in that one column, that one variable, a lot of missing data, and you decide to just replace all of them with the mean for what was there previously, then you have a lot of that column will suddenly be just the mean value, right? All the same. So the variance of that data will shrink very, very tightly to whatever that mean was, and it'll make it seem kind of like really synthetically, really fake, that the data comes from that, like really tightly around that particular mean value, where it really isn't, right? The data should have been distributed, but like now, I don't know, 50% of my data is just that one mean value. Like it's a crazy flattening of the data space into like one really focused point. You can also create like unrealistic blobs. If you're doing this in terms of the class-specific imputation, you'll create these blobs that are like these segmented clusters that are just very unrealistic. Unknown, like one of the first things I mentioned was you can replace like missing data with just like the word unknown, and then you can handle it in your code or in your modeling afterwards. But this now becomes a different category. Maybe not all unknowns are created equally. Maybe there's different kinds of ways that these missing data were kind of obtained or not obtained, I guess. And they weren't all obtained in this one unknown way, right? But calling all these instances unknown as if it's one type of unknown is simplifying things too much. That's not good. And it can distort relationships between variables as well. So here's a regression versus interpolation. This can be used for filling gaps. So there's two ways that we can draw a curve through data points. The first one is regression, where we just fit a single function through all the data at once. So this is like you've probably seen this in your spreadsheet applications. You have all your data, you have a single line that goes through it. Okay? And these lines won't necessarily like touch all the data points. It's sort of like an average that kind of represents the overall trend of the data. And this is fairly good when there's lots of noise and the data points you have are kind of scattered all over the place. Now you have a single line, like a function that goes through all of your data, so that if you're looking for a value of what I'm calling x now, that you don't have, you can still make a prediction as to what it should be, and that prediction is based on this regression line that you have. Okay. Interpolation is different than that. Interpolation is when you construct a function that does actually pass through all of the observed points, but it's kind of built locally. So imagine having 2 points side by side in your data set. You kind of just connect those 2 points, like you basically connect the dots sort of thing. You just kind of, like when there's 2 points side by side, you just connect them with a line, and the overall result is sort of a jagged function that goes through the entire data set. So now if you have 2 points that are fairly close to each other, and you expected to see a value of x somewhere between them, you can still estimate what that is because you have like this line that connects those points, and you can still and